Hello students, so let us start with a little bit of octave programming, and octave is very much similar to Matlab. So in our last few classes, we have seen how to enter a matrix in octave and how to access an element of that matrix. Like you can enter a matrix like this: 1, 2, the first row, and 2, 3, 2, first row, 2, 3, the second row, and A11 will be A1, and in this way you can access all the elements of the matrix. And if you put A1 comma colon, then the full first row will be shown, and if you put A colon 1, then the full column will be shown. So it is very nice, very convenient to manipulate with matrix in Matlab or octave. So Matlab is actually a matrix laboratory, so you can do a lot of things with matrices. So, and you can also, if you want to change A11 to 1000, you just write this and the whole matrix will be like this. So and one very in all programming languages, loops are of great importance. So in Matlab there are many types of loops, but we will concentrate on the for loop. The for loop is widely used, and the syntax is also very simple, and you can always use help. I think help like this, help for. Oh, this is not the correct syntax. This help for, and you can access the octave help. So this is the octave help. So this is an example. You can see the example. So for I equal to 1 to 10, that means I will be incremented starting from a value of 1 to a final value of 10 in steps of 1. So for I, then this I, that means if you write something without a semicolon after it in Matlab or in octave, simply the value will be printed on the command window. So this is similar to print I. So see also par, for, do, while, these are also looping commands, but we'll be using this here. Will not make any use of do or while. So we'll learn about the essentials of Matlab and see how the finite element operations can be done in Matlab. Okay, so we have seen for loop, and if you want, you can use. So suppose you want to give a series of commands here, and also frequently you want to use those series of commands. So it is not always convenient to write the commands here repeatedly. So what you can do, you can open the editor and you can write the commands here. You can save it in a file and you can run it. Suppose so this is a new script. So let us see this CLC. CLC means clean the command area, then clear all. That means all the variables. These are not mandatory. Clear all. Clear all means all the variables here in the workspace which you used previous to this will be cleared, so that no garbage remains in the workspace. Then suppose I write for I equal to 1 colon 10, then end for, that means this is the loop, and I say I use some other directory, so G colon n class. So this is the current directory. So now I save the file. Save file. So the file will be saved in class, and you have to give some name. Suppose I use this as xxx1.m and I save it. So the file is saved with the name xxx1m in this folder. Now you can run the file, save file and run. So if you run it, so and you again open the command window, the values of I will be printed in the command window. Okay. Also you can use a say 3 here I J, and you remove this one. Let's see what happens. And if you save and see, this I is stored here as stored here in the workspace. See, I is stored here in the workspace. So once you run this code, this CLC will clear this workspace, and whatever is written on the command window will also be cleared by this CLC command. So now if you run, you can use also end or in place of end for. So run. So let's see what has come in the. So there is some error is coming syntax error. So we have made some syntax error. So this may be the syntax error. Here all for I equal to 1 to 10. Oh, another end should be there for J. So this end for will be end for. Let's see whether it runs now. Run, save file and run. Yeah, it has run. So it is giving I as 5. Oh, so it starts here. I1, J1, then I1, J2, I1, J3. The J loop has ended. Then I2, J1, I2, J1, I2, J2, I2, J3. 2 has ended. I equal to 2 has ended. Now I equal to 3. So you can think it of as a J loop running within the I. So taking I as 1, J1 to 3. Taking I as 2, taking I as 2, J1 to 3. Take I as 1, J1 2, 3. Taking I as 2, J1 2, 3. Okay. So as if you are accessing the matrix rows one by one, and within first you are considering the first row, then I is the row number and J is the column number. So you are accessing as if you are actually not accessing, you are actually going through all the rows of the matrix. First take one row, for that row you go through the columns, then go to the second row. For that, for I stands for row number. Go to the next row and then go through all the columns of the second row, then go to the third row, then go through all the columns of third row, and likewise you are moving. So this is called a nested for loop. Okay. So now with this we'll see what we are trying to do in this lecture. So actually we have seen assembly of two string elements. We want to write a program which will assemble our elements. So see, so we can assemble manually. How we can assemble? So this is the stiffness of element 1 and this is the stiffness matrix of element 1. So this 1 means the element number. and this is the stiffness matrix of element 2. This 2 is the element number. So now what is the stiffness matrix of this? K1 minus K1 minus K1 K1, and the stiffness matrix is K2 minus K2 minus K2 K2, where K1 is this stiffness, K1 is this stiffness, and K2 is this stiffness. Now what we do? Locally this is first row, first column. So this is the row number 1 1, first row, first column, 1 2, first row, second column, 2 1. See the blue numberings: 2 1, second row, first column. This is 2 2, second row, second column. But where are they? These are the local numbering for these elements. This 1 2. But where are they in the system? In the system also they are in 1 and 2. But this is not true for this element. For this element, local numbers are 1 and 2, but 1 has actually gone to 2 and 2 has gone to 3. So here the 1 has to be replaced by 2 and 2 has to be replaced by 3, and same thing here. So here the blue 1 1, actually the blue 1 1 in this element is blue 1 1, but the actual place of this blue 1 1 in the system stiffness matrix will be 2 2. So K2 will go to 2, and this is actually the assembly process, and you now are in a position to do it manually. But how can this be done in a computer program? So for that we bring in one array which we call LDOFs. Okay, LDOFs. You can give any other name. So we have called it LDOFs. That means element degrees of freedoms. So the first this is a two-dimensional array, as you see, and the first index is the element number, and the second index is the local DOF number, and the value of this is the system DOF number. Like LDOFs 1 1, that means for element 1, local 1 has to be replaced by system 1, and for element 1, local 2 has to be replaced by system 2. But for element 2, local 1 has to be replaced by system 2, and the local 2 has to be replaced by system 3, system DOF 3. So now suppose for this element 2, I am considering the 2 1 entry, that means minus K2. Then where will it be in the system stiffness matrix? 2. So this local 2 means system 3. So this will be in third row, and 1. So local for element 2, local 1 means system 2. So it would be in the third row. This 2 for this 2 3, for this 1 2. So it has to be in the third row and second column. So in computer, the statement will be this K, capital K, stands for the system stiffness matrix. So K LDOFs 2 2, because there is element 2, so 2 will be there for it. So element 2, this 1 will be replaced by, sorry, element 2, this is element 2, this 2 will be replaced by LDOFs 2 2, that means element 2 local DOF 2, and this element 1 has to be replaced by LDOFs 2 1, because this is 1. For this one, for element 2, the 1 has to be replaced by this, and since this term can also come from some other element, so whatever is existing there, that plus this has to be added. So see here, that means K2 1. So for consider element 2. K2 1. That means this 2 has to be replaced by LDOFs 2 2, element 2 local DOF 2, and 1 element 2 local DOF 1, and we will automatically get 32. So K32 will be like this, and K33 means this, and that means the K element 2, the local DOF 2 will be replaced by system DOF 3, element 2 local DOF 2 replaced by system DOF 3. So this will go, this term will go to this place 3 3. So this is the logic, and now I will show you how to write the Matlab code for this. Now let us start writing the Matlab statements for this problem. So for this problem, first, since there are 3 degrees of freedom, you have to, this K suppose is the system stiffness matrix. So K is zeros 3 by 3. So this is K. So you notice one thing. So when you put a semicolon after this, the output will not be shown on the command window. But if you omit it, then it will like this. Okay, and your this K1 will be, as you know, 1000 minus 1000 minus 1000 1000. This is the stiffness matrix for the first element, and this is the stiffness matrix of the second element. Okay. Now LDOFS. So LDOFS for the first element, we write it like this: LDOFS for the first element. So this stands for the first row and all the columns is equal to a row vector, and that row vector is 1 2. So, and LDOFS for the second element, it is again a row vector, and that is 2 3. You can put comma, no problem. So LDOFS is like this. Okay, so LDOFS 1, if you type LDOFS 1, that will give you the system degree of freedom for 1 and 2. For element 1, it will give you the 2 system degrees of freedom. The first one is the for local first degree of freedom, and the second one for the local second degree of freedom. And LDOFS, this will give you, so for element 2, the first one will give you the first local degree of freedom is number 2 system degree of freedom, and the second local degree of freedom is number 3 system degree of freedom. Now if you write, where goes for element 2, where goes this to 1? Where goes this to 1 for element 2? Where goes this blue to blue 1? Second row, first column. That is minus K2. But where does it go? So K2 to 1 is minus 2000. But where does it go in the system? So you have to write in the system it is 2 1. That means LDOFS for element 2, the local degree of first one is 2, that means 2. Then LDOFS 2 second element, and local degree of freedom 1. So the local degree of freedom. So the second one is the local degree of freedom, and here the second one is the local degree of freedom. That means this 2, this 1, and this first 2 is for the element. So that must be equal to K2 2. So this is how. So have I made any mistake here? Oh, I have not given this bracket. So Control C will exit this, and so I have missed out one bracket here like this. So reduce to bracket close, this bracket close here. So that's why it was expecting the bracket and it was standing still. I pressed one Control C to come out of it. So see, this minus 2000, that means second row first column of K2 has gone to third row second column of the system stiffness. But this is not sufficient, because some other contribution may come at this place from some other element. Then this will be simply overwritten by the new contribution. So what we do is we put this, copy, right mouse button click, copy, you bring the cursor here, and here you paste, and here put this. So that means whatever is existing at this location, that will be appended with this, or added with this. Okay, that means K32 will be this K221 plus had there been some other contribution from some other element. So what was already there in this location. So this is what was already there in this location plus K221. So see, in this way we can put all the entries in proper places. But just in the command window doing like this is difficult. So what we do is we do it in a program. So new script. So here we write clear CLC. CLC means clear the command window, and clear all, that means clear all workspace variable. Then here, so here what we do is, so we do it like this. So we do it like this. The stiffnesses, so let us write the stiffnesses of the springs. The stiffnesses of the springs are T1, or let us write 1000 and 2000. Okay, we are not putting semicolon here because we want this to be written in the command window for checking purpose. So stiffnesses, that is the spring stiffnesses like this. Okay, the first spring has a stiffness of 1000 and the second spring has the stiffness of 2000. Then the system stiffness matrix is zeros 3 by 3. That is the number of degrees of freedom. And LDOFS is, for the first element it is 1, 2, and for the second element it is 2, 3. So let us save it. Save file as maybe somewhere here, not in the administrator. So you can change this folder to class. Okay, so file, save file as Here you give some name xxx say 2, it will be set. So now suppose we are placing suppose we are placing the second element. The second element stiffness is 2000 minus 2000 minus 2000 2000. Okay, good. So you can just save file and run. If you run, you can see command window. Okay. Oh, this is the command window. So the stiffnesses are 1000, 2000. K is set as K is the system stiffness matrix, and it is set as a 3 by 3 null matrix. LDOFS, the system degrees of freedom numbering, this is for the first element, this is for the second element, and K2 is the stiffness matrix of the second element. Okay. So these are the variables K, K2 in the workspace, K, K2, LDOFS, stiffnesses. Now we just start a loop for I equal to 1 to 2, 1 to 2, for J equal to 1 to 2, and from here, yeah, okay, I'll write it again here. So I was thinking of copying it from there. So K LDOFS, this is for element 2. So element 2 local degree of freedom I, comma LDOFS element 2 local degree of freedom J is equal to K I J. That means I and J are the local numbers, so say they vary from 1 to 2. So this I and J will be here, and this K2, and this I and J are the local numbers, and LDOFS 2I, that is the system degree of freedom number for this I for element 2, and LDOFS 2J is the system degree of freedom number for J for element 2, local degree of freedom number J of element 2. But as you know that this is not sufficient, because we have to add it to the already existing content. So here you put paste plus, okay. And each step will be printed on the screen. I think it's okay. So let's try it out. Run, save file and run. So in the command window, see what is coming. This is what we got earlier. So K. So first I equal to 1, J equal to 1. So this is copied here. Then I equal to 1, J equal to minus, J equal to 2. I equal to 1, J equal to 2. Then I equal to 2, J is over. I equal to 2, new J. I equal to 2, J equal to, I equal to 2, J equal to 1. So it is here. And this it has not printed. Why? I do not know. So let's see what is. Oh, this is here. This is I equal to 2. This I equal to 2. J equal to 2 is here. So this is how whole thing is done. But what about K1? So what we do here is we put it inside another loop for element number. L say for element number 1, we have two elements. Elements number 1 to 2. Tab. We are writing it in a nice nested way. So this end is for this for, and this end is for this for, and another end required. And will also work. Okay, so this is in a for end. Okay, so but what we will do here, this is the not I num, this is the L num or the element number. So why have we done it? For the first element, see the stiffness value is 1000. So we can write K element is equal to stiffnesses. Okay, let us write K equal to K value, say K value equal to stiffnesses 1. Okay, and K element is equal to K val minus K val minus K val. So this is the stiffness value when I see for this will be a loop on element numbers. So when element number is 1, this will be the stiffness of, this will be the first stiffness, and the element stiffness is this, and this K2 will be replaced by K element. So what is the advantage of this? Well, when for second element, K val will be taken as 2, and this K element will be for the second element. So now this is not required. So there is a loop over element and one change. So here it is 2, but here now it has to be given as L now. So L. So I think now it's okay. So let us run it. Run, save file and run. So it's running again. So now the command window. Oh, there is an error. Stiffness is undefined near line 10, column 8. Maybe we have made some. Oh, here is there. Okay. So here I run, save file and run. Now I think it's okay. So it starts here. Stiffness is K. Now K2 is not there. LDOFS K first. Now it is entering the loop. So for the first element, the stiffness is 1000. The element stiffness matrix is this, and this element stiffness matrix is getting added up one by one. See the beauty. Now it is okay. Here one mistake is there. Just a minute. So this is the element stiffness matrix. This over. Now the second K value is also taking there. It is taking as 1000, but it should be 2000. So what is the wrong here? So it should not be stiffness is 1. It should be stiffness L. then how can it take element 2? Every time it will take element 1. So now run, save, and now see the comment window. So now this is the full element 1 has been given, has been added up. So now the second element is coming. This for the second element, this is the element stiffness matrix. Now one by one, first here the contribution from second element has come, then it has come here, then it has come here, and finally it has come. So you get the system stiffness matrix. So this is the assembly procedure. Now you can, if you want to add other element, you just put the stiffness value of the next element, and you increase the system stiffness matrix size. You give the L2Fs of the third element, and here Lnum will be up to the number of elements. If you add one spring, then it should be 1 to 3. This is okay, and all the things will get assembled. So you have to calculate for, suppose for 3 springs are there. For 3 springs there will be 4 nodes. So 3 springs, another spring stiffness value will come. This K will become 4 by 4. This will become 1, 2, 2, 3, 3, 4, and this will be from 1 to 3, and this same process will be executed, and the element stiffness matrices will be added up. So thank you for your patient hearing.